Hello everyone, welcome to this video tutorial on finite element analysis, a practical approach using ANSYS. This is Shankar, Assistant Professor, Mechanical Department from Tyagaraja College of Engineering, Madurai. So as I always say, in order to solve any problems in any FEA softwares, right, you can follow these general steps. So the steps can be classified into pre-processing, processing, and post-processing. So the majority of our work lies in pre-processing. Almost all the steps from defining the problem, element selection, defining material properties and section properties, modeling the problem, meshing, and deciding the boundary condition, all this pretty much comes under pre-processing, which is the work of the user. The solution stage is to be done by the computer. Then once we solve our problem, we will be able to view our results using post-processing tools. Right? So this is going to be a series of video tutorials. So we have already completed our first exercise on analysis of deformation and direct stress in a stepped shaft. You can find the link below. Right? So today's exercise is going to be analysis of deformation, member forces, and stresses in a simple truss. So this is going to be our second exercise, and we will follow all these exercises in our subsequent video tutorials. So my problem definition for today's exercise is going to be this truss. So we know truss is a structural member which is used to support the loads, say for example in bridges or in cell phone towers. So you can find trusses. So most of the truss will have a combination of triangular shape. The triangular shape is the most rigid structure form. So we'll use this triangular shape to build our structure. There are also pretty much other shapes in building a truss, but basically it is used to support a load. Here in our problem, I have a truss. So one end of the truss here it is fixed, which means it cannot move. This point cannot move in any direction, x, y, z. In all the direction it is completely arrested. Whereas at the other end I have a roller support, which means it can move along x direction, but the other two direction y and the perpendicular direction z are arrested. And I have a series of loading conditions. I have three vertically downward loads at the bottom, 45 kilonewton, 60 kilonewton, and again a 45 kilonewton. And I have two inclined loads at the top, 8 kilonewton inclined at an angle of 45 degree and 10 kilonewton inclined at an angle of 30 degree. So this is a one-dimensional representation of a truss. But as I said earlier in my previous video tutorials, everything in nature is basically 3D. But for the purpose of analysis, and we'll simplify the 3D problem into one-dimensional problems. So this is also a 3D problem. Then definitely it must have an area. So all the truss members, so this is a member, all these line represents each and every single member made of a particular material. All these are rigid members. So the cross section of all these area are constant, which is 1000 mm square. And also in a truss, all the members will be pretty much made by the same material. There will not be different materials as in case of a stepped bar. So let me consider my truss is made up of steel throughout the all elements. So the Young's modulus and Poisson's ratio are given for steel. So my aim is to determine the reaction forces. So I am going to have pretty much reaction force at this fixed end, and also I am going to have a reaction force at this roller support. So I am going to have two vertical reactions, and also due to this inclined load can be split up into a series of vertical load and horizontal load. I can resolve this inclined load. So due to these vertical loads, I have three vertical loads here, and I'll have two vertical loads here. So due to these 5 vertical loads, I'll have vertical reaction at this fixed end and at this roller end. Similarly, this inclined load will also be resolved into horizontal load. This horizontal load will have a reaction, horizontal reaction at this fixed end. So as you can see, this is a roller support which can move along x direction, due to this horizontal force, it may displace by certain amount. Hence, there will be a horizontal reaction at this location. So we have to find these reaction forces and member forces. So the forces that we apply are being transferred along these members. So this can be called as members or frames. Right? So transferred along these members or frames to the fixed ends, to the supports. Right? So truss is usually used to support the loads. Hence, we are going to find the forces in each and every frame of this given truss. And ultimately, if there is a force, then definitely there must be a stress concerned with it. Hence, I am going to find the stress in each and every members and also the overall deflection. So, I'll compare my results analytically and numerically by using FEA software. So, this is my problem definition. So, what I'm going to do now is that I'm going to simplify the problem in such a way that it is very much easy to solve in ANSYS. So the difference between both the slides is that here I have the length units of the each and every frame, or not all the frames, but along this bottom frame you can find the length unit. So this is 6 meters, 9 meters, 9 meters, and again 6 meters, and the corresponding angle are given. So using this angle, so I have a 6 meter here, I have an angle here. With these two, using trigonometry, I can find the height of this frame. Similarly, I have a 9 meter here, I have a degree here. Using these two, I'll be able to find the height of this member. As I find this height, I can resolve all these length units in terms of coordinate values of each and individual points. So that is what I have done here. So taking this first point to be 0, 0, 0. So as I have this 6 meters along this direction, so this point would be 6, 0, 0. Then I have a 6 here, I have a 9 here. Put together, it becomes 15 meters at this node. Similarly, I have calculated the coordinate values of all the points. So this is what I have done in the problem definition stage of my analysis of this analysis. Okay. So the second step, so it is going to be the element selection. So this is first step actually here. It's not second step. I have to just change it to step 1. Okay. So step 1, it is problem definition basically, and step 2, it is going to be element selection. So as the problem has been converted to 1D, so this problem is a one-dimensional problem. So it's basically a 2-dimension. But all the elements that I use is a line element. A line is a 1D element. So hence I'm going to use, so as the problem has been converted to 1D, it pretty much means that all the members are lines and a line is a one-dimensional element. But this problem is actually in 2D, right? So don't get confused by the word what I have put here. So it means that all the members in the problem are line. So a line is a 1D. So that is what I mean here. So in order to construct this problem, I will use a 1D element. So in ANSYS, we can find two 1D elements. One is a link element, another is a beam element. In previous problem, as you can recall from our stepped bar analysis problem, you can find that I have used a beam element. Right? Here I am going to use a link element for this problem. So we'll use link element. Under the link element, there's a subcategory called as 3D finite strain, and the code word for this element is called as link 180 in ANSYS for this exercise. So pretty much about link 180 is that it is a 3D pole element. So here the element 3D means that it can move along all the 3 directions. It can be used along X direction, Y direction, and Z direction, right? And a variety of engineering applications like modeling trusses, cables, links, springs, etc. It is a uniaxial tension compression element with 3 degrees of freedom and no bending of the element is considered. This is important part of link element. Whereas in beam element will have tension compression. In addition to that, it will have bending and shear. Whereas link element will have only tension and compression. So it will not have any bending. As you can see that a truss will not have bending in any of its frames. If there is bending, then there is a severe failure of the truss. Hence, a truss will not bend at any cost. In each and every member of the truss will not have bending, will only transmit tension and compressive forces alone. So hence, I have neglected the beam element and I am using a link element. So I am going to select this link element. This is the end of step 2. So the step 3 is going to be material properties and section properties. So already the material properties are given here, or else you can even find it from this table, and also the section. So usually the section we are going to define it under the link section and add a new ID, and we are going to define the area alone, which is given in the question as 1000 mm square. Right? So this is pretty much summarizes the third step, and the fourth step, modeling the problem. So this is my existing problem, which I have converted into this stage by denoting all the joints in terms of coordinate values, and I have the fixed locations, and I have the loading conditions with all my data. So this is the problem. Now one more thing, consider this inclined load, right? So I can rewrite this inclined load as, so I'll just show you. So consider this is a 10 kilonewton load acting at 30 degree. This 10 kilonewton in red can also be represented as a 10 kilonewton in this blue, using the concept of principle of transmissibility of forces. Similarly, the 8 kilonewton in red color can also be represented as 8 kilonewton in blue color, using the concept of principle of transmissibility of forces. It pretty much means that a force can be transferred to any location along the same line of action. So line of action should not be differing. So along the same line of action, I can shift my force anywhere. Right? So this is the principle of transmissibility of forces. Using this concept, I can change my load from 10 kilonewton to this blue color, and here 8 kilonewton from this red to blue location. So once I change this, my problem will get converted to like this. So here, this is nothing new. So it pretty much means the same thing what we have done before. But there is a reason why I have done this, because ANSYS, the arrow mark is represented only in this direction as it is shown in this slide. It will not be represented like this in upward. So in order to get very much closer with ANSYS, I have converted this red color loading condition to this blue color loading condition. Right. This is pretty much modeling of the problem, but there is a variation that I am going to induce in this system. So before getting to know what is the variation, I'll just tell you what it is. So the step 4 is going to be the modeling stage, and step 5 is going to be the meshing stage. So now what I'm going to tell you is that, what if modeling and meshing can be done at the same time? So that is what I'm going to do. So in order to understand this terms, right, consider a problem which is a line, right? So a line has two endpoints, so that points are called as key points in ANSYS, as you are familiar with that, right? So I have key point 1 here, and I have key point 2 here, and I have a center line which is L1. This is my problem, this is my model, right? Now this is the modeling of the problem. After modeling, I'll mesh this problem. Say, let me say I'm going to divide this element into 7 individual elements. So hence I have divided the problem into 7. So 7 subsegments. So you can find it here: E1, E2, E3, E4, E5, E6, and E7. Once the problem gets converted from this ordinary to this element, so this stage is called as meshing, where the problem gets converted from ordinary to a FEA problem. Once it gets converted, each element will have 2 endpoints, and that is called as nodes. So I have pretty much have 8 nodes here. This is the usual conventional way. Now what if I change this? What if I change this? Instead of doing these 2 steps, instead of doing this first 2 steps, what if I model the problem as elements? So pretty much means that, so initially you will keep a key point here, you'll keep a key point here, then you will use a line to join. What if you keep a node here, if you draw a node here, and I draw a node here, and I directly draw an element here? Okay. So this is pretty much equal to dividing this line into one element. So modeling the problem, and if you pretty much divide this problem into one element, it gets to this point. Right? So instead of doing this 2 stages, I'm going to combine it into one stage, such that in modeling, instead of drawing the key points and joining them with lines, I'm going to draw the nodes, and I'm going to join those nodes with elements directly. This will avoid doing the meshing stage, but this is not very effective method in all the cases. The reason why I am doing this in this problem, in this Truss problem, is that in each and every member I can model it as a single element. I don't need to I don't need to divide this each member into many elements. The reason being that along a particular member in a truss, the force is going to be a constant one, and hence the stress is going to be a constant one. Even if you divide it into any number of elements, the stress is always going to be the same. It is not going to vary along the length of the element, and hence in order to avoid the computational time, I can model it as a single element, which will give me the same result as in the case when this line is subdivided into many elements. So it will avoid the unwanted computational time that is spent by ANSYS. Right? So what I'm going to do, I hope you can understand here. I'm going to model the problem instead of keeping key points here, joining them with lines, and then going for meshing stage, and then dividing them into number of divisions, and then meshing. I'm directly going to draw this problem as, instead of key points, I'll be keeping nodes at all these locations, and instead of using lines to join these points, I'm going to use elements to join these nodes, which I have drawn earlier. This is what I'm going to do. So my modeling and meshing stage at the same time gets converted to like this. So my problem is going to be like this, and each and every point 1, 2, 3, 4, 5, 6, 7, 8, and 9, all these 9 points are now represented in terms of nodes, and each and every line, it is going to be of only one element. I'm not going to subdivide this line into individual elements. I'm going to directly draw element here. So this is what modeling and meshing is going to be done at the same time. So you don't need to mesh again, because as you have, the meshing is the stage where ordinary problem gets converted into a FEA problem. The ordinary problem, you will have lines, points, areas, and volumes, but once it gets converted into a FEA problem, you will have only elements and nodes. So in this modeling stage, I am directly drawing the elements, which will avoid me to do the meshing stage. So the meshing stage actually consists of these 3 steps. In this problem alone, in this truss problem alone, I can avoid this meshing stage because I have already drawn element in my modeling. I don't need to go for meshing. So the final step is going to be the boundary conditions. So I have load at 5 location, and I have 2 boundary conditions. So these are my 7 boundary conditions, which I have to give it as an input data. So once I give these 7 input boundary conditions, so the fixed boundary condition means that the u of x, the translation in 3 directions are 0, and in roller support means the displacement in y and z is arrested, but in u of x, the truss can move. So I'll consider this direction to be x, this direction to be y, and the perpendicular direction to be z. So hence the roller support, the truss can move along x direction. And finally I'll apply the forces in whatever direction I want. Here there is also a small variation there because I have an inclined load. So this is a new variation. Now how to apply this inclined load? So that we have to see. So we'll see one by one. So we'll see how to solve this problem in ANSYS. Okay, so this is what we are going to do. Now I'll open ANSYS APDL window. So you can find here, we'll have this window black screen here. Okay. So initially what we would do, we would go for preferences, click on structural, and I'll click on OK. So this is what I will usually do. And the next stage, I'll go to element type, I'll go to add, edit, and delete. I'll click on add. So I'm going to use a link element and 3D finite strain 180, and I'll click on OK. Then I'll close this. The second stage, adding material properties. So that would be the next step. So I can come one by one. So already we have defined the problem very clearly. So the second stage would be the adding the element, which I have done now. I have added the link 180 element, so you can find it here. I have added the link 180 element here. Okay. So the next stage would be to add the material property data. So my problem, I have the material as steel with Young's modulus Poisson's ratio given in the question, and I have a section property of 1000 mm square. So I'll add one by one. I'll add the material properties. I'll go to material models, structural, linear, elastic, isotropic. I'll give 200 gigapascal. So as I told you already, you can recall that ANSYS is a black box software. It does not keep a track of its unit system. It is the duty of the user to keep the unit system throughout the problem as a constant one. So here what I will do is that the forces are represented in kilonewton and all these length units are represented in meters. So one thing I'll do is that I'll keep all the units as meters, the length units as meters and the force unit is as kilonewton. So hence here 200 gigapascal means 200 into 10 to the power 9 pascals, which is 200 into 10 to the power 9 Newton per meter square. So I have to apply it as kilonewton. So hence I have to minus 3. So 200, 200 into e power 9 will give you Newton per meter square. I have to apply it in kilonewtons. So in order to apply it as kilonewton, I'll put it as 3. I'll minus 3. So 200 into e power 6 kilonewton per meter square. I have applied it in the unit of kilonewton per meter square, and the Poisson's ratio, as it has no unit, I'll apply it as 0.3 and click on OK. I'll close it. So I have defined the material properties. Then going for section properties. So in previous case we did go for beam because the element we added is a beam, but here we have added link, so I have to go for link. I'll click on add. So I'll give an ID as 1 because I have only one section through the entire problem with the same cross section area through the problem as 1000 mm square. So hence I'll add only one ID. Okay. So it is asking for a section name, so I'll just give something as circle or whatever you want. Just give some names. And area, so you don't need to give a radius or diameter or something. So maybe I can even rename this to be section SEC. I'll just give it as SEC. And the link area, it is given as 1000 mm square. Again I have to apply it in the terms of meter square, so I'll apply it as 1000. If you convert the mm square into meter square, it will have E minus 6. So this is going to be a Newton per it is going to be a meter square data. So 1000 mm square. So if you convert it to meter square, you will multiply it by 10 to the power minus 6. So 10 to the power minus 3 is for 1 mm to meter conversion. So mm square to meter square conversion, you will multiply it by 10 to the power minus 6. And I don't need to give this data added mass, and I don't need to change this tension and compression. It pretty much remains the same. I'll click on OK. So this completes my step number 3. So I have completed the material properties and section properties. The next step is modeling. But as I told you, I'm not going to directly model with the help of lines and key points. I'm directly going to model with the help of elements and nodes. So nodes and elements are pretty much the thing that I'm going to model. So I'll add all these coordinates, but instead of keeping key points, I'm going to directly add node at all these locations. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 nodes. There are totally 9 nodes in my problem, which I'm going to add one by one. So in order to do that, go for modeling, create. So click on nodes, click on inactive CS. So the first node number is 1 and the first coordinate, so first is 1 and the corresponding numbers are 0, 0, 0. So I'll do it one by one. So 0, tab, and 0. So I'll add it. So forget about this rotation angles. Don't give anything at here. Just give the location values and the coordinate numbers and the node numbers and click on OK. So one is created here, but as the coordinate system is here, you can't see that one is being created. But anyway, I'll create the 2. So here my 2 corresponds to 3, 4, 0. So as you can see that all these units are in meters. So the initial problem, it is given as in meters. So I'll get to the initial problem where you can find, see, it is a 6 meters, 9 meters. As I already told you, ANSYS does not keep a track on unit system. So for this Truss problem, I'm going to keep the force units to be in kilonewtons and the length unit to be in meters. So I'll just directly input it as in terms of 3, 4, 0. So the second location is going to be 3, 4, 0. So I'll just click on OK. So you can find the second node to be created here. Similarly, go on, keep on adding all these 9 nodes. So I'm not creating key points. Be careful with that. I'm not creating key points. I'm directly creating my nodes here. So 6, 0, 0. That is pretty much my third. Again, one more important thing is that don't forget to change these node numbers, or else it will get overwritten. So if you keep the same number as 2, and if you just click it as 6, 0, 0, and if you click on OK, this 2 location will get changed to its new location that you have given. So don't forget to change this node number. So 3 and OK, you can find 3 created here. then the point 4, which is 10.5 comma 9 comma 0. So I'll give it as 10.5 meters comma 9 comma 0. So I'll keep on adding it like this. So next, okay. So this is the thing that I have done wrong. So you can see I forgot to overwrite it as 4. Now the 3 point has moved to its new location. So I have to redo that again. So I'll change it to 6 comma 0 comma 0 and I'll click on OK. So this is the third point. So don't forget to change this number to 4. Now I have to input it as 10.5 comma 9 comma 0. That is pretty much my fourth node. So don't forget to change the node numbers. So I'll click on OK. So now we can find the fourth node being created here. Right? So if you overwrite, this 3 will go here and it will get vanished from this location. So be careful while overwriting, while changing these node numbers. Now my fifth is going to be 15 comma 0 comma 0. So it is going to be my fifth nodal points. Okay. Then I'll go to my sixth node point, which is going to be, I'll just look it here, which is going to be 19.5 comma 9 comma 0. Keep that in mind. 19.5 comma 9 comma 0. So that is going to be my sixth nodal point. I'll click on OK. So I can find 6 created here. Okay. And seventh nodal point, which is 7 here is 24 comma 0 comma 0. So it's going to be 24, sorry, not 234, it's 24 comma 0 comma 0. Click on OK. So the 7th nodal point is created here, and the 8th nodal point 27 comma 4 comma 0. I'll click on ANSYS 27 comma 4 comma 0, and I'll click on OK, and I'll click on this one. I'll click on, see, I have forgot to change it to 8, so now the point 7 has been moved to its no location. So 8 is 24 comma 7 comma 0. I overwrite this. I have overwritten this 7 with this new coordinates, so I have to change that again to 24 comma 0 comma 0. So 24 comma 0 comma 0. So only then it will get back to its new location. So again, coordinate number 8. It is now 27 comma 4 comma 0. Okay, 8 is created, and finally 9th coordinate point is going to be 30 comma 0 comma 0. So that is going to be my 9th point. So don't forget. So see here, this is my 9th point. Don't forget to overwrite the 9. Okay, 9. Okay, I changed the node number. No problem. So pretty much I have created nodes here. You can find at the top it is nodes, not key points. As in the earlier case, these are not key points. I have directly created the nodes, which is the result of meshing stage. So I am doing the meshing stage in modeling itself. This is what it means. Now in order to join all these nodes, so nodes are the things that will appear only after meshing stage. Once the nodes are appeared, each nodes will get connected only by elements, not with lines or areas and any other stuffs. Nodes and elements are the only thing which will be the result of meshing stage. Now I am doing the meshing stage in modeling itself. Hence, I have to join all these nodes with the help of elements only. In order to do that, go for create elements. In our problem, we are lucky that all our stress, it is of uniform area and uniform material. Hence, we need not do a stage called as attributes, mesh attributes. That stage we can just skip the stage, because all the elements, it is of same material and cross section. There is nothing as different. Say this is going to be of steel and this side it is going to be of aluminum. We don't have that variation of materials or cross sectional area. Suppose, consider that if you have a variation in material data, so what you have to do is that initially, before creating the elements, you have to set that attributes here. Click on the set attributes, click on the corresponding material and corresponding section number, then click on OK. Then you have to create the element. So in order to create element, under the element you have a section called as auto number. Click on that, and you have a subsection called as through nodes. Click on this, and as you do for lines, click on the 2 nodal points, click on OK, and an element will be created here. So I'm going to pretty much create. So this is my element 1. The element 2 connects 2 and 3. So I'm going to do my second element through nodes, I'm going to connect 2 with 3. Okay, so you can connect elements in any order as you want. After completing this, you can create elements here, you can create elements here. In any order you want, you can create elements. But I'm going to follow this numbering that I have given in this diagram. So I'll follow pretty much the same. So I've created the second one. The third one is 1, 2, 3. So this is not compulsory one, but in order for comparison, I have named these elements in this diagram. So pretty much I'll follow the same in ANSYS 2. So I'll connect 1 with 3. Okay, so through nodes 1 with 3, I'll click on OK. Then I have the fourth element is 2 to 4, that is my fourth element. So through nodes 2 to 4, I'll click on OK. This is my fourth element. So suppose if you have my fifth element, say it is going to connect with 4 and 3 but with different material cross section. Now you have to go to change to element attributes, change the material or section number, whichever is changing, click on OK. Now if you click on true nodes and join these two, it will join with the material and material or section number that you defined in attributes. Now in this problem I am having a uniform material and section. I don't need to bother about these attributes. Okay, so I'll add the fifth element which connects to 3 and 4. Okay, and that's my fifth element. Sixth element is going to be 3 to 5. So that is going to be sixth element. That is 3 to 5. It is sixth element. And my seventh element is going to be 5 to 4. 4 to 5. That's my seventh element. So 4 to 5 and click on OK. And keep on doing this until the entire problem is completed. And make sure that the lines, the nodes you join are actually in the problem. Maybe say consider I don't have this element, I don't have a line joining 6 and 4 in the problem itself. Don't do that. So some of the students usually make this mistake that there are lots of lines connecting in a truss, and there may be some lines which do not connect with each other, right? So but students unknowingly they connect those 2 points which are not even connected in the actual problem. So don't do that mistake. So I have connected this, I have completed this stage, I have completed the 7, and the 8th will be 5 to 6. So I'm connect with 5 to 6, I'll click on OK. Then 9, it is going to be 4 to 6, the topmost one. So 9, sorry, I get it wrong. So 9 is 4 to 6, I'll click on OK. And after 9, 10, which is 6 to 7, that is 10. So again, as I told you, I'll just recall that this ordering is not necessary as what I'm doing. You can do it in any order if you want, but I have given the numbers here, so I'll pretty much follow the same thing. So 11 it is going to be 5 to 7. 11 is going to be 5 to 7. Okay. Then after 11, 12, which is 7 to 8. 12 it is going to be 7 to 8. And finally 13, 14 and 15. So this is 13, 14 and 15. So 13, I'll click on apply, 14, apply and 15. So you can, instead of clicking OK and going again and again, you can click apply to do a continuous set of connections like this, right? So I have completed all my 12 elements. So now you can switch on the element numbers to see whether it is only 12 elements. So go for plot controls, numberings, in the element or attribute numbering, click on element numbers and click on OK. So but I can't find any elements here, it has disappeared. The reason being that the display mode it is in nodes, right? In order to view the elements, you have to change this display mode from nodes to elements. In order to do that, go for plots, click on elements. Now we can find. So 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12, 13, 14 and 15. So you can find here I have 15 elements, E1 to E15. The same I can find it here also, right? So I have pretty much completed my stage of modeling and meshing at the same time, right? I have created elements on node directly in the modeling stage, which pretty much even completes my meshing stage. So directly modeling and meshing are completed. Now the only thing left is to apply the boundary condition. So please don't mesh this problem again, it will not get meshed, and don't get confused, because in the meshing stage is the stage where ordinary line problem gets converted into elemental FEA problem. Here I have directly drawn the element in modeling, which neglects the need for going to meshing stage. But you can't do this in all the problems. only in this problem we can do the meshing along with the modeling stage. Even if you do the same in this problem, the results will be very much accurate. But if you do follow the same procedure for even a step 2 problem, your results which will not match with the analytical solution. So please be careful about that. So I'll go for loads, I'll define loads, I'll apply. So initially I'll apply this boundary condition fixed location to node 1. So I'll apply structural displacement. I'll click on not on key points because you have never created any key points, you have created only nodes. So on nodes, I'll click on this first node, I'll click on OK. So it is going to be pretty much all DOF. So all the diagram has been arrested. I'll click on 0 and OK. So all the things get arrested here. And in this location, I have a roller support, which means that the roller support means the displacement in Y and Z is arrested, but in X the truss can move, because here the X location is in the horizontal direction. I'm going to keep it as horizontal, in which the truss can move. So except X, I have to fix the remaining two directions. So again on nodes, I'll click on this node, I'll click on OK. Instead of all UF, I have to select only UI and UZ. I can pretty much leave all the things unselected. I can click on OK, which will apply a roller support at this location. So I have applied the two supports. Now I have to apply the individual loading conditions. So I'll start with this inclined loads. So the inclined load cannot be directly applied in ANSYS. So this is the point. Please remember this. Inclined load cannot be directly applied in ANSYS. Only either a vertical load or exactly horizontal load in either positive X or negative X, positive Y or negative Y, but only vertical or horizontal loads can be applied. The inclined loads cannot be directly applied in ANSYS. So in order to apply this inclined load, first initially I will consider this 8 kilonewton and 10 kilonewton to be acting in vertical direction only. So initially I am going to assume these two loads to be acting in vertical direction, and I am going to apply the same here. So I'll do that. So for that you have to go for force or moment on nodes. So the 8 kilonewton, it is going to act at this point. So I'll click on this point, I'll click on OK, and it is a f of y. I'm going to assume it to be in vertically downward direction. So it is in y direction and it is in downwards. So I'm going to consider this 8 kilonewton acting vertically downwards. So it is pretty much going to be minus 8. So please be careful. I'm going to keep the force unit is in kilonewton. I have applied the Young's modulus in kilonewton per meter square. Hence, I have to keep this force unit as kilonewton. So I'll just apply minus 8. I'll click on OK. So you can find a downwards arrow mark here. Now, I have to convert this vertical downward load to an inclined load. In order to do that, I have applied the load in a node, correct? So this load will get connected with that particular node. So if I just rotate the node here, the load will also get rotated along with the node. So I'll again repeat. So I have created node at all these locations. So in this location, I have applied a load at this node. I have applied this downward force at this node. I have an option to rotate this node. So if I rotate this node, this force will pretty much get rotated along with the node. So I have to rotate the node 45 degree in anti-clockwise direction, right? So that is what I am going to do. In order to rotate the node, the option for rotating the node will be available under modeling. So I'll go back to modeling. I'll close the loads. I'll come back to modeling. Here I'll close the create. Here you can find under the category of move or modify, you have an option called as rotate node CS, which is coordinate system. This is a node coordinate system. So I am rotating. Click on this rotate node. You have three or four options here. I'll click on by angles because I know the angle to be rotated. So 45 degree in anti-clockwise direction. So I'll click on by angles, and it is asking for which node to rotate. So I'll click on this node. I'll click on OK. Now the node to be rotated is 4. So as I have selected here, now I have to rotate about the axis. So I'm going to rotate it about the perpendicular axis. This is the x axis. I'm not going to rotate about x axis or y axis, but the perpendicular axis to the screen, which is z axis. I'm going to rotate the load about z axis. So only then it will get rotated correctly, right? So about z axis, the angle is to be 45 degree. But please make sure that the angle that you are giving here, it always denotes the clockwise direction by default. So if you give only 45, it means that this load 8 kN in downward direction is rotated 45 degree in clockwise, but instead it has to be rotated in anti-clockwise direction. Hence, I have to apply a negative sign here. So the values that you give here are by default in clockwise direction. In order to rotate it in anti-clockwise, give a minus sign. Now click on OK. See, you can't find any change in load, still it is downward direction. That is because the screen has not refreshed yet. To refresh the screen, just click on your mouse roller button, just go for, just see, you can see, I can just zoom in and zoom out, the screen has refreshed, and you can find, I'll just zoom over this location, right? You can use this tool zoom model to zoom to a particular location, draw a border around, draw a box around this point. See, the arrow mark has been inclined by 45 degrees. So you can see to the vertical, the arrow mark has been inclined by 45 degrees. So this is how you apply an inclined load in ANSYS. So I'll use this fit view to fit the, you can find the arrow mark being rotated. Similarly, I'll do the same for this 10 kN. I'll initially apply it in downward direction, then I'll use 60 degree clock counterclockwise. Uh, so I'll use the 60 degree here to apply it in inclined position. Right? So this is what I am going to do. So 45 degree, it is actually in clockwise direction. I think I mentioned it wrong before. Please forgive me. So this 45 degree, it is in clockwise direction. So ANSYS rotation, it will be by default, it will be in anti-clockwise actually. So that is one thing I mentioned wrong. Please forgive me for that. So initially I'll apply the load and I'll just correct my statement here. So I'll apply the load, define apply force or moment on nodes. So this is going to be my on nodes. I'll click on this node, I'll click on OK. Initially I'll apply it in downward direction, but it is instead of 8, it is going to be minus 10 kN. I'll click on OK. So it is, I have applied it in downward direction. I have to rotate the node in order to convert this vertically downward load to an inclined load. For that, I'll go to modeling under the move or modify category under rotate node CS. I'll use by angles and I'll click on this node and click OK. So in previous case I mentioned it wrongly. Please sorry for the wrong information. But the angles that you give here by default it takes anti-clockwise, not clockwise, right? So if you give 60 degree, it is anti-clockwise direction. In order to give it in an opposite direction, in order to give an opposite rotation, that is in clockwise, you have to apply minus. So if you apply minus 60 degree, then it means you have to rotate the 10 kN in clockwise direction. But here I have to apply the 10 kN in anti-clockwise direction. So that's my 10 kN in anti-clockwise direction. So this is clockwise, 45 degree in clockwise, this 60 degrees in anti-clockwise. So a small misconception there. So I'll click on OK. So again you can't find any change. So once you just rotate the mouse button front and back, the screen gets refreshed and you can find an arrow mark lying adjacent to this line 3 rotated at an angle of 60 degree. Right? So I have applied these two inclination loads. Now I'll apply these 3 vertical loads, which is very much easy, 45, 60 and 45. So now I'll go to loads, apply force or moment on nodes. I'll click on this node and this node, because I'm selecting 2 nodes at the same time because the force is same and the direction is same. So I'm selecting both the nodes at the same time. I'll click on OK. F of y direction, so it is downward, so hence the minus sign, and it is 45 kilonewton. So kilonewton is going to be the force unit throughout the problem, so I'll give it as minus 45. Click on OK. So 2 loads of minus 45 being added here. So on nodes, I'll click on the central node, I'll click on OK and minus 60. So that is my central load point here. I can find this minus 60 and click on OK. So this pretty much completes all the steps in pre-processing stage, which is the last step of boundary condition, which I have completed. So the next step is solution, which the computer does for us. So I'll directly go to solution, I'll just solve my problem, I'll click on current errors and I'll click on OK. So you can find within a moment it gets solved, right? So now I have to see the results using post-processor. I'll compare the results one by one. So I have already done the analytical calculations for you. I have calculated the reaction for this problem. using analytical solutions, right? I hope would be very much familiar with this analytical solution. So we can see that I have three reactions here due to these three vertical downward load, and also I have an inclined load which can be resolved into a vertical and horizontal load. Due to all the vertical loads, I will have two reactions R1Y. So at node 1 I have a Y direction load, and R9Y again I have a vertical Y direction load here. And due to the horizontal component of these two inclined loads, I will have an horizontal reaction R1X at this location. So in order to find the values of all these reactions, I've done these calculations here. You can go through this calculation using any strength of materials or engineering mechanics book. You can find these calculations pretty much easier. So my final answers are going to be these three things, right? So in terms of Newton, they are here, but I have solved it in kilonewton. So the answer would be 81.13 kilonewton, 79.525 kilonewton, and it is 3.003 kilonewton. These are the answers that I need to be expecting from ANSYS. Let me see whether these answers coincide or not. Okay, in order to see the reaction results, go for list results, click on reaction solution, then click on all items, let it be by default. Okay, click on OK. You can find a notepad file. You can find the three values. F of x, it is minus 3.0034. In actually I have solved the entire problem by keeping the force unit in kilonewton. So the final answer is in kilonewton. So f of x is minus 3.0034 in node 1. So similarly in here you can find, so in 1 in x direction, the answer is minus 3.397 Newton. If you convert it to kilonewton, it is 3.003 in kilonewton. So the same can be found here. The minus sign pretty much means it is in opposite direction. See, here the reaction, here the reaction is in leftward side, hence the minus sign. So don't get confused by the minus sign, just see the magnitude. The magnitude is pretty much the same. Again, similarly here 79.526, 81.131. Same results can be seen here. 79.526, I can just, it is round off, and 81.131, this 0.8 gets round off here, which is 1. So 81.131, 79.526, and minus 3.003 kilonewton. So I can find a very much accurate values getting compared with ANSYS and analytical solution. So this is the first thing that I have to find. The second thing I have to compare with analytical is the member forces, the forces which are present in all these members individually. So now we are going to compare the member forces in ANSYS with the theoretical value. In order to see the member forces in ANSYS, you can't find it directly. In order to do that, you have to do a little bit of a coding. So for that, so what you have to do is that you have to find the coding in order to find the member forces. To do that, there are two ways. The first way is open ANSYS help and find out what the coding is. So go to ANSYS and you can find ANSYS help here 19.0. Click on that. A document opens like this. So this is the first page of the document that will open. In the search menu, click on, type the name of the link. Type the name of the element that you are using. In our problem, we are using an element called, as link 180. So this is the name of the element. So in our problem here, type link 180 and click on the search button. You'll get a search tab like this. In this search tab, you can find the first option as link 180. Click on that, you'll get a document like this. So this document pretty much summarizes all the description about link 180. So what are all the inputs needed, what are all the loads it will take, and as you come down, you can see what are all the outputs that you can get from this link 180. So among these all the different outputs, we are interested about only two. One is the member forces and the other one is stress. So find here the member force and the axial stress. So we are interested about to see about axial stress, because in truss we'll have only tension or compression, and the stress created due to tension and compression is only axial stress. So hence keep this in mind, force and SXX, keep these two in mind. And now come down. As you come down, you will find another table. So I can find force, right? And the corresponding coding is SMIC1. Similarly, for stress, we have found it as SXX, and the corresponding coding is LS1, 2. So for stress, it is LS1, 2, and for member forces, it is SMIC1. So this is how you find the coding to find member forces and stress in a link. So earlier in a stepped bar, we used this same similar type of coding to find the stress for our beam element. So similarly, you can find the same here. I just forgot this to tell you in our earlier video. So similarly, we use beam 188 element. So type beam 188 and click on enter. So it will take a moment to search, and here click on this beam 188. You will find a similar description data for beam 188, and as you come down, you will find the table column where you'll see all the outputs of beam 188. Just come down. Okay. So here you can find, so in the last step bar problem, the stresses are axial stress. So find the word axial stress or direct stress. So whatever it is fine. Click on here. Axial direct stress, and the corresponding wording is SGIR. So note this corresponding word and come down. You'll find another table. In this table, look for that SGIR, and the corresponding coding is SMIC 3136. So these are the codes that we used for our stepped bar. So this is how you look up this coding for calculating the stress. The main reason that we are using the coding is that we are drawing the problem as 1D, and we are trying to find the stress which requires area. So you can find stress equal to load by area, and the area is needed to calculate the stress. But in 1D, you can't have any areas, so we are just defining the areas in section. So what this coding does is that it takes the area from our sectional properties that we have defined earlier, and it will apply to our problem and will calculate the stress for us. So that is the function of this coding, all these things. So now we are using link element, so I'll close this beam element for time being. So we are going to use LS1, 2 for stress and SMIC1 for force. So keep this in mind. So now first we are going to see the force. So the coding is SMIC1. So in order to apply the code, go for ANSYS. Now go for general post processor, and under element table, click on define table, click on add. Now come here, come down, click on SMIC sequence number SMIC and type 1. So SMIC1 is the coding for force. One more thing I would like to tell you here is that this ANSYS help viewer, it is available in latest version. For old version of ANSYS, you can open up this document by simply typing. For the time being, I'll just close this. By simply typing in this command prompt, type help, comma, name of the element, which is link 180. If you just type this and click enter in old version of ANSYS, you will find a similar help menu opening up like this, and from there you can infer all this data, right? Okay. So now for member forces, I have to add it as SMIC1, and for stress LS1, 2. So three things that I have to add. So I'll add it one by one. So define, add, click on SMI by sequence number. In that SMIC, click on 1 and OK. Now I am going to add LS1 and 2 as well. I'll need that for calculating the stress. So LS1, OK, and add. Come below. So find by sequence number LS2. So these are the three things that are needed for. So SMIC1 is for member force, LS1 and 2 is for stresses. So I have added all the three. So I'll see one by one. First I'll see the member force. So in order to see the member forces here, go for plot controls, contour plot. Under line element result, click on that. So in both these things, keep it as SMIC1, which is for member force, and click on OK. So you can find some colored blocks overlapping with each other and telling you what is the member force in each member by the corresponding coding, color coding that you can find at the bottom. So save this image. So in order to save the image, you know that, go for plot control, write meta file, and invert white or black, and give a suitable name, right? So give a so this is member force, so I'll give the name as force, and I'll just save. Okay. So, but this is a little bit uh, clumsy and I can't find the individual results very clearly. So in order to see the individual results very clearly to compare with that of the analytical solution, I'll go for list results under element table data, click on that and click on SMIC alone and I'll see. So these are my 15 elements and the corresponding member forces. Right. Now this is a pretty much easier, which I can compare with my actual values. So the minimum value is minus 101.41 and my maximum value is 73.284. And all these individual values, you can compare it with the analytical solution. So I have already calculated the analytical solution. So here it is. So these are my axial forces at all the 15 location. But this frame IDs does not correspond to the frame ID that I have given in ANSYS. So you just have to match up these results with this results. Say for example, my value of maximum value is minus 101.41. So let me compare it here. The maximum value among all this is here. See, minus 101.41. So approximately up to 0.2 digits. The ANSYS is very much accurate. So you can find here minus 101.41 at 14th frame. So 14th frame means here in our model we have given the 14th frame as, so this is the 14th frame joining 8 and 9. This is the 14th frame which has the maximum compressive stress of minus 101.41. So this shows us minimum value because that's a negative sign, but this is the maximum compressive stress that it means. So we can find it the actual values. I'll just zoom over here. Okay. I have solved it and I have just listed the results. There is a detailed calculation procedure in order to solve this. So this is the axial force in kilonewton and newton, but my answer is in kilonewton, so I'll use the C. So minus 101.41 here, and here you can find this same minus 101.41. And the other value, which is 73.284, I can find the same thing here, which is 73.284. 283649. It is accurate up to 6 digits, but in ANSYS it is showing 3 digits. Similarly, you can compare all these values. So again at frame 6 you can find 73.286. Here again at frame 6 you can find 73.284. Similarly, compare all this value with this values. So just bring it almost bring it here, right? Minus 99.407, minus 99.407, 33.136, 33.136, 62.64. So keep on comparing all these things, exactly matching with the analytical solution. So this is how you compare all this value. So in order to save this file, click on Control A and copy all this. Right click, maybe you can use Control C to copy this data. Open a notepad file. Notepad file. Click on notepad and Control V, and all these values will be listed. Control S and save it as force values. Save it as in a particular folder that you have created for exercise 2. Save it as force.txt, which you can later refer for any further more data. So we have compared the force. Similar way, I have the stress results too. So I have my stress results in Newton per mm squared. I have my stress results, but in ANSYS the stress results will be in kilonewton per meter squared, because we have given the unit as kilonewton for force and for length unit as meter. So the answer is going to be kilonewton per meter squared. In order to see the stress result in the same colorful plot, I have to go for plot results. Click on contour plot again. Line element result, LS1 in first box and LS2 in the second box. So element table item at node I, click on LS1, and element table item at node J, click on LS2 and click OK. Maybe the color may not change, but you can find the change in values. So stress is nothing but force divided by area, as the area is common in all the member forces. So all the members, so each force gets divided by a common factor of 1000 mm squared in our problem, right? So you can find the stress values in kilonewton per meter squared. So again, this may save this image by going for plot control, write meta file and invert white or black, and save it as stress, SGRESS. So it is in my folder FA Practicals Exercise 2, so I'll save it here. So again, it may look little clumsy, so I need to list down the individual values. In order to do so, go for list results and go for element table data. Instead of SMIC, click on LS1 and LS2 and click OK. So you can find these stress results in kilonewton per meter square. So compare it with here. So here it is in Newton per mm squared. So the digit may vary, but the values are pretty much same. See here, minus 99.407. Here minus 99,407. So this point is due to here Newton per mm squared. Here the unit is in kilonewton per meter squared. But the values are same. So you can find from top till bottom. You can find pretty much the same values. So again, copy Control A and copy all this and open a notepad file and save it as stress list. So go for Control B and paste it and save it as, so instead of force, give it as SGRESS, stress list. Save it as. So I have saved the force result, I have saved the stress result, and I also have to save the reaction solution, which I forgot. So I'll click on OK. Again, copy all this, right? Put it in a notepad. Notepad, right? And paste it here. Control S, and this is my reaction. Or reaction. I'll save it as reaction. So now, so far we have compared the forces, we have compared the stresses, we have compared the reaction. So these are the pretty much three things which you have to compare analytically and numerically. But one thing which you can see only in ANSYS and which you don't need to compare analytically is the deformation. So I can see it by the help of deformed results, deform plus undeformed, and click on OK. So this is the deformation result, which is 0.019107. It is in meters. So convert it into mm, you'll get 19.107 mm is the deflection here. This value you need not compare it with the help of analytical solution. Just see it in ANSYS, that is enough. So in order to see this in colorful plot, go for contour solution, node of solution, click on DOF solution, displacement vector sum, and click on OK. So you can find the colored plot of this stress value, deflection, deformation, right? Save this too. So go for part control, right meta file, not vector black, and click on deflection and save this. So you are going to save the force, you are going to save the stress and the deflection images, and you are going to save the force list, stress list, reaction in a notepad file. So this is pretty much that you are going to do in this Truss problem. So this pretty much summarizes and so we have come to the end of our Truss problem. So I hope you have understood the Truss problem very well. If there are any doubts, you can always contact me. So one more thing I'd like to tell you is, so you have a Truss problem. Each one of you have an individual problem. You can solve that. And in order to verify that whether the analytical solution that you have put are correct, so there is a website which will be helpful for you. I'll just tell you, it's called as, yeah, here is the website. It's called as www.federicobongfigley.com/entrustsolver.expx. So what you have to do is that you have to draw the truss here. You have to apply the loading condition. The only thing is that here you can't apply the inclined loads. So inclined load should be transferred as should be resolved as horizontal and vertical loads here, and you can apply it and pretty much draw the same thing. And you can click on the button solve, which will be at the bottom of this page. Once you click the solve button, so you can find the deflection. So you can find the deflection and the individual forces here, right? So we can see it in the image. At the same time, you can see it here. So this is the summary of the results that you get. This will be helpful for you to compare your analytical solution, whether you have done anything wrong or whether the analytical solution is right or okay. Right? Once you correct your analytical solution, you can compare that analytical solution with the help of the ANSYS results, which is pretty much the same for our problem. So thank you guys. So I'll just sign off now. So until I see you in another video, okay, in our next exercise, I'll meet you again. Signing off is Shankar. Thank you.